will have 9. Bloody hell. So 3, 6, 9. Okay, so there are 9. 3, 6, 9. And then the height is going to be 6. Okay, so 3, 6. And then I'm going to draw up to here. Okay. And I would like to pinpoint this location. Okay, I like to pinpoint that location because when later on when I draw everything, right, you realize that it will pass through that point. So what do I mean? So I'm going to draw separate points now. So the separate points I'm going to draw. Okay. So from one end of the corner, I touch the other end. Okay. And where it touches is important. It's going to touch at the midpoint, and this is at one end. Okay. And then the other point. This software is, I think it's the user or the software, I think it's the user. Okay. Again, you guys are fooling around. Okay. And then we're going to construct another point. So this is 2, 4, 4.5. And then this is going to the other end. Okay, if this is drawn properly, it's like pulling out teeth. And then the other end will intersect the midpoint somewhere around here. Okay. I'm going to be, okay. So what you realize, if all the points intersect, and if I draw a vertical line down the centroid, so this point is what we call the centroid. If I draw it down, it will exactly intersect that point. Okay. So that's where the distance from here to here, right? So this is where the distance from here to here is 3. And the distance from here to here is 6. The entire distance is 9. And if that's the case, I call this L. This will be 2/3 L. And this will be 1/3 L. Okay. So that's where the equivalent load will be acting at this position. So the equivalent load will be acting on this location. Okay, so that's the reason why. So now you know why now. Okay, right. Any questions so far before I go on? Anyone? So you guys have no question, means you're good. Anyone? Okay. So I hope you're all still there. Can someone say we are here?
Yeah, we're here. We're here.
Okay. Damn it, man. This is lonely, man. I thought my lonely days are over. No, it's just the beginning. Right. So I'm going to copy this. And then I'm going to come over here. I'm going to paste this in. Okay. So now you understand everything now, how we get the equivalent load. Okay. So by looking at this free body diagram, okay, so we have 1, 2, 3, 4. So the number of unknowns, okay, the number of unknowns is we have 4. Okay. So from here, when you have 4 unknowns, okay, if you apply static analysis, okay, when you apply static analysis, right, when you apply static analysis, okay, you can only form 3 equations will be formed. Okay, will be formed. So you only can get 3 equations, right? Why 3 equations? Because you use summation of forces in the X, summation of forces in the Y. For this case, summation of forces will be absolutely useless. And then you summation moment about Z. Okay. So you only will get, for this case, not even 3, you only get 2 equations by using static analysis. So therefore, from here, you realize that the structure, right, the structure cannot, okay, the structure cannot be solved. Okay, I don't know how to spell cannot now. The structure cannot be solved using static analysis. You realize that this is not going to work, right? So you are going to apply, okay, we're going to apply static analysis together with elastic deformation. Okay, so what do I mean by elastic deformation? So elastic deformation means we need to apply deflection is equal to PL over what? AE. That's what it means. Okay. So now let's look at static analysis. Okay, let's look at let's form the 2 equations, right? So we know that this distance is equal to 4 meters now, right? Because it's 2/3 times 6 times the length, right? So we're going to do static analysis. So from static analysis is that you have summation about moment in the Z direction, and you're going to do your static analysis at point A. Okay, so what it means is you are going to, where I'm drawing the circle now, that's where you're going to take your moment from. Okay, so the equivalent load is going to generate anti-clockwise direction. So this will be equal to force. Sorry, it's going to be plus. Okay, multiply a distance of 4. Right. Then you're going to have your plus by 25 kilonewton. This is the load at the top, multiplied by entire length of 9. Then you will have your FB. Your FB is going clockwise, minus by 6 FB. And then your FC is going clockwise, so minus 9 FC. The whole thing will be equal to 0, right? Then when you factor everything in, you sort things out, so you get 240 times 10 to the power 3 plus by 2 to 5 times 10 to the power 3 minus by 6 FB minus by 9 FC. The whole thing will be equal to 0. Okay, so you write down 6 FB plus by 9 FC. The whole thing will be equal to 465 times 10 to the power 3. So this is your equation number 1. Okay. Then you form your next equation. Summation about forces in the x direction is equal to 0. Okay, so equal to 0. So you will have your AX plus by your FB plus by your FC minus by your equivalent load, which is 60 times 10 to the power 3, minus by your the other load, which is equal to 25, and equal to 0. Then over here you will have AX plus by FB plus by FC, and the whole thing will be equal to 85 times 10 to the power 3. So this is equation 2. So I'm going to do everything for you, okay? So we do summation about forces in the y direction is equal to 0. So we can say down here is AY is equal to 0, okay? So now let's consolidate what we have, right? So what we have are two equations, two useful equations. However, how many unknowns you have? 1, 2, 3. So you have 3 unknowns. So that's where we call this structure statically indeterminate. Okay, so this is a typical example. So the next thing we're going to do, when there's a case, we're going to apply, okay, we're going to analyze elastic deformation of the cables. Cable B and cable C. Okay, so why cable B and cable C? Why did we pick these two? Because if anything will be under elastic deformation, will be cable B and C. We already assume that member ABC is what? It's a rigid body. When it's a rigid body, means it does not what? Deform. Okay, so the only way to do this is to consider cable B and cable C. So I'm going to write down here that member ABC is assumed to be rigid. So i.e. no elastic deformation. So there's nothing to do with elastic deformation of ABC. You can't do anything because you assume it to be what? Rigid body. Okay. So the next thing that we have, so we're going to analyze the deformation of the cables at B and C. Okay. So now when we do elastic deformation analysis, you have to be careful. It is no more static analysis already. Okay. It's no more static analysis. So elastic deformation, when you do this, when you go into elastic deformation, so we're going to apply that deflection is equal to PL over what? AE. So this is what we're going to use, right? And the notation that we're going to use is tension, right? When it's tension, the stress, the deflection, the strain, and the force are all what? Positive. When it's in compression, the stress, the deflection, the strain, and the load are all what? Negative. I want to highlight this. This is important. Why? Because we just did what? We just did static analysis where we say positive